Om Sri Sai Ram. Welcome back to the third session of this chapter, Magnetic Effects of Electric Current. In the last session, we have discussed about the force acting on a current carrying conductor, and we find out using left hand rule, Fleming's left hand rule, the direction of force experienced by current carrying conductor, right? In this chapter, we'll learn an interesting topic, the application of that force which is acting on current carrying conductor. Alright, that instrument which we invented in early 18th century is electric motor. It's a very ingenious machine. We'll discuss in this lesson. But before diving into today's chapter, today's topic, let us go and answer a few questions which I have given in home assignment in the last session. What was our first question? In the first question, it was given that you have a bar magnet, you have a current carrying conductor, and you have a magnetic field around the current carrying conductor. We asked you that what is the direction of force experienced by current carrying conductor, whether it is in the direction of magnetic field or opposite to the direction of magnetic field. We already know when you have a bar magnet and we have a current carrying conductor, there is an action-reaction phenomena, right? Because bar magnet exerts a force on current carrying conductor exerts a force on bar magnet. If you have a north pole of bar magnet here, if you have a current carrying conductor here and current is from down to up, what happens? The field lines will go through the bar magnet. So bar magnet will experience a force outward direction. If you have current carrying conductor, if you have a north pole of bar magnet, so the force direction will be outward on the bar magnet due to current carrying conductor. What will be the reaction? It will be just opposite to the direction of the magnetic field line, right? Because the bar magnet here is coming out. Now, if I am fixing the bar magnet, what happens? The current carrying conductor should be experiencing a force inside the board. That's what we discussed last time. So, let us see what we have the answer. A current carrying conductor has a magnetic field lines around it, yes or no? For suppose this is the current carrying conductor, I direction, you have a magnetic field line around it, right? Now I put a bar magnet here, the north pole is here, south pole is here. Now what will be the direction of magnetic field? In this direction. Now what will be the force experienced by the external magnet, this north and south, this bar magnet, will be outwards, right? According to the definition of magnetic field line, the north pole will be experiencing the force in the direction of the magnetic field. Now if I hold this magnet, what happens to what will be the force exerted by this magnet on this conductor? Opposite direction, right? If it is coming out, this bar magnet should go in according to the Newton's third law. That's what we have written here. When the magnet is fixed, when I fix this magnet, according to Newton's third law, the wire experiences a force in the direction opposite to the direction of the magnetic field at the point. So at this point, what happens? The magnetic field line is outside the board and the force experienced by the bar magnet is outside. I am keeping this bar magnet fixed, I am leaving this, so it should go in. That is the reaction. If the force experienced by the bar magnet we call as action, I am holding it, I am leaving it, the reaction force will be inside the board. Understood? So this answers your first question. Now let us go to second question. What is the second question? I have given you this diagram. The electron is moving in this fashion and the magnetic field is given in this direction. What will be the force experienced by this electron? Right? So we have already studied in the previous chapter what is the direction of current. It is opposite to the direction of the motion of electrons. If the electrons are moving in the downward direction, what will be the direction of the current? It will be upward direction. What is the direction of magnetic field given? In this direction, right? Now, we have to calculate the direction of the force experienced by this electron. Recall the Fleming's left hand rule, right? Recall the Fleming's direction of the force is perpendicular to the direction of the magnetic field. What is Fleming's left hand rule? See here, force experienced by the conductor. Here it is electron. Okay. Now the force, the magnetic field lines. Given the magnetic field line is from left to right. So the forefinger shows the magnetic field direction. Now current as we discussed, the motion of electron is downwards. So the current direction will be opposite. That means upwards. So magnetic field line in this direction, current is in this direction. Unfold your thumb. It will be into the page, right? That's what the force experienced by the electron in this magnetic field. So the direction of the electric current is opposite to the direction of the motion of electrons as we discussed. Therefore, the force is directed into the page. Alright. This answers your two questions in the last session and also summarizes what we have discussed in the last session. Right? In this session, we will solve some examples related to this, so we will get a hang of what we actually discussed in the last, to get a habit of doing this, because force, magnetic field and current direction using left hand, so Fleming's left hand rules will become tricky. It will come naturally when you keep on practicing. One way to remember it is FBI. You just remember FBI. F comes the force, B is the magnetic field, and this becomes the current. So if you keep on practicing, it comes naturally when you do the problems. Right? We'll start with some problems and then go further to discuss the concept, the main concept of this session. Alright? Some more examples. Current is passing through a conductor in the given direction. Find the direction of the magnetic field at the points A and B. This is point A, point B. He is asking, what is the direction of magnetic field at the point A and point B due to this current carrying conductor? Now, we know this current carrying conductor will produce a magnetic field around it. And the direction of the magnetic field line will be given by right hand thumb rule. Put your thumb towards the direction of current and curl your fingers. The direction of curling of your fingers will give you the direction of the field line, magnetic field line. So I'm curling the fingers. So what happens? The field lines will go inwards and come out, right? So it will be like this. Right? The field lines will be like this. It will come outside the board. Through B it will go inside the board, and through A it will come outside the board, forming a circle. Alright. So at B, what is the direction of magnetic field line? Into the board, right? So whenever we discuss the magnetic field is going inside the board, we denote with this symbol. A cross mark and circle it around. At A, what happens? It goes inside and have a semicircle and comes outside through the point A, right? When the magnetic field is coming out, that direction will denote as like this, a dot and a circle. When the field is going in, we'll denote with this symbol. When the field is coming out, we'll denote this with this symbol. So at A, what happens? The field line is coming out. At B, it goes in. So this is the symbol. So it answers your question. At B, the magnetic field line is going into the board. At A, magnetic field line is, direction of the magnetic field line is coming out of the board. That means what happens, if you put a north pole here, it will experience a force outside the board. If you put a north pole at B, it will experience inside the board. You have to understand both the places I am putting the north pole. Okay. If I put the south pole here, it will go inside because it is opposite to the direction of the magnetic field. If I put south pole here, it comes in the direction of the force will come out. So this is how you will define the magnetic field line at point A and point B, the direction of the magnetic field line. Alright. So let us go and discuss the next example. What he gives, oh, this is a beautiful experiment. This is a setup. The current is moving in clockwise direction around the coil. Give the direction of the force experienced by the conductor at different points of the coil. Let us see where the current is uniform. Current is uniform in this segment. Current is also uniform in this segment. Current is also uniform in this segment. Right? We can ignore this segment because you can see this magnetic field line and also the current are parallel. So the force experienced by this line will, due to the external magnetic field, is negligible. When you find the force on this segment and on this segment, it will be enough because it is in between. The force acting on these two segments will act in such a way that it satisfies this segment. So no need to worry about what is the force in this segment. Let us concentrate on these two segments. Let us give them names. A, this is B, C and D. Now concentrate only on the segment AB. What happens? The current is going from down to up, right? So according to left hand rule, the second finger gives you the direction of the current. So it is going from down to up. North pole is here, south pole is on the right side. How does the north pole field line direction goes? From north to south, right? So this gives you the magnetic field direction. Forefinger is giving you the magnetic field direction and this is giving you the what? Current direction. Now unfold this thumb. What happens? It will go inside. So this AB is experiencing a force due to this magnetic field inside the board. Alright. Now see here, your basic intuition should tell you that AB current is in upward direction here. There CD current is in downward direction. For both of the segments, the magnetic field direction is same. From north to south, here also the magnetic field direction is same. Here also magnetic field direction is same. The only change is the change in the direction of current. When you have change in the direction of current, that means what should it be? The direction of force should also change, right? That means if it is going down, it should come up. Let us cross verify with Fleming's left hand rule. Magnetic field direction is from north to south and now the current direction is from up to downwards, right? Right, like this. Now unfold your thumb, it comes outside the board. This CD segment experience the force outside the board and this AB segment experiences the force inside the board. So this is all one body. This is called a coil. So one segment of the coil is experiencing the force inside the board, other segment of the coil is experiencing the force outside the board. So we'll explore this in more detail in this session. Just see and embrace this setup. How ingenious is this setup and the use of this setup we will discuss later in this session. So this is how we identify the force experienced at different points in the coil due to this external magnetic field, which is provided by these two magnets, north pole and south pole of the same magnet. Okay. Now let us go to our today's topic, and in this chapter we started with this question, right? Who is ringing the bell? Who is turning the fan? I am switching on the fan, but somebody is turning the fan. It seems that somebody is turning the fan, but nobody is going physically and turning the fan. Who is turning the fan? If you ask anyone, they will say this answer, which is a theoretically, yes, it's correct. Electrical energy in the wires are converted into mechanical energy of the fan. So it is right, because it is rotating. I am providing electricity. Somehow it is managing it to rotate itself. But the thing is, we need to understand how it actually happens. I am providing electricity, yes, but it is kind of doing something to rotate the objects. How it is doing? Right, so, well, how exactly it is doing? Now, again go back to Fleming's left hand rule. Can we use Fleming's left hand rule so cleverly to make the things rotate? Just think of the last example. You take a single coil and the force at both ends acts in different directions, right? Because we change the direction of the current in different segments. If the force is acting differently on the same coil at different areas, that in opposite direction, the force is acting on opposite direction in different areas in the same coil, that means what we are doing? We are trying to rotate it, right? If this is a body, if the force is acting in upwards in this edge and another force is acting on this edge downwards, what is making this object? So this force will make it move up, this force simultaneously will make it move down. So it is helping in rotating, right? So let us go and explore in more detail how can we use this left hand rule to make the object have a full rotation. All right. That thing, that equipment which is rotating using electricity, we call as electric motor. So let us go and explore the function of it. This is the setup, beautiful setup. Again, by now it may be common to you. The field direction is from, magnetic field direction is from north to south, right? The current direction, it is a positive terminal, it is negative terminal. For instance, as of now, just ignore this part, okay? Just ignore this part, just concentrate on this coil, that's it. Now, this positive end is attached to this segment AB and negative end is attached to this segment DC CD. Alright. Now, we pass the current. What is the current direction? Current direction is towards inside the board. This, let us see, AB is inside the board, CD is coming outside the board. Okay. Now, we know the current direction, we know the magnetic field direction. Let us find out the force. It's very easy, right? Again, take your left hand. Field direction is from north to south and the current direction is inwards, right? So this AB, the coil AB, the segment AB will experience a force downwards, right? This is direction of magnetic field north to south. The current AB segment is inside the board, right? So the thumb comes down, the unfolded thumb, it comes down, it shows the direction of the force. So this segment AB is experiencing a force downwards due to this magnetic field. Okay. Now same, let us draw like this, for instance. Okay. For this point of time, when it is at this point. Now, just observe the segment CD. CD current is how the CD current goes from A. The current goes from A to B, B to C, C to D, right? So the current here is opposite to the direction of AB. From A to B the current is going, that means it is going inside the board. Now it is coming from C to D, thus it is maintaining a closed loop. Now when it is coming outside, still the magnetic field direction is same from north to south. Now what happens, what change you expect here? The only change you expect here is direction of force. The direction of force on AB is downwards, the direction of CD should be intuitively upwards, right? Let us again cross check it. Direction of magnetic field is from north to south. Use your forefinger, and your second finger will give you the direction of current from C to D, that is outside the board. Now unwrap this thumb, it gives you the direction of force. So this direction of force tells that this segment CD is experiencing a force due to this magnetic field upwards, right? So one end it is experiencing a force downwards, other end it is experiencing a force upwards. So what happens? It rotates. It is helping it to rotate, right? Now when it reaches this highest point, what happens? It has to come down, right? To form a full circle, what happens? It has to rotate, it has to go up and come down. Go up and come down. So to form a full circle, one segment has to go up half a circle and come down half a circle, right? Here we saw why the segment AB is going up, segment CD is going down. Because the force is, why the segment AB is going down, CD is going up? Because the force is acting on AB is downwards, the force acting on CD is upwards, that's why you are able to rotate the coil. Now it reached its maximum position. Now CD has to come down, AB has to go up. So how can we change the direction of force now? Just think. Here why the AB is coming down, CD is going up? Because the change of direction of current, right? Here AB is experiencing this current inside the board, that's why it is experiencing force downwards. Now CD is experiencing the force outside the board, that's why it is experiencing force up, right? To experience a force downwards, we need to have the current similar to AB, right? That means CD should behave as AB when it goes up, and AB should behave as CD when it goes down, so that it will have the current upwards, it will experience a force upwards now, it will experience a force downwards now. Do you understand? Because this AB current is going down and it has to rotate, it has to complete a cycle. To have a further rotation, it needs to have a force upwards now. It can't go any more down. If this segment is AB, if this is AB and this is CD, CD is going up, AB is going down. After this, it has to come up to rotate. So it needs to experience a force upwards. Until now it is experiencing a force downward, that's why it is down. Now it has to experience a force upwards. That means it has to change the direction of current, right? That's how we change the direction of force, because magnetic field direction we cannot change, it is fixed. Only thing we can change to direction of force is direction of current. There this ingenious instrument split ring comes in role. What it does, you can see here. This is how split ring is. If you zoom it in, it takes this shape. So what is this? This is a split ring. This we call a split ring. This whole thing. Okay. So this two are we call as brushes. This one we are talking, this one. These two are brushes. So these are stationary. One end of the brush is connected to positive terminal and another brush is always attached to negative terminal of the power source. Alright. So what happens when this segment, let us suppose this segment is AB segment, this segment is CD. Okay. When this segment, now in the start how the current goes, current comes from this brush positive and goes from AB, comes from CD and completes the circuit, right? Now because of this, the AB experiences a force downward, CD experiences a force outward, it rotates. Now when it rotates, these rings are attached to this coil. So when this coil rotates, these rings also rotate and this brush stays still. When this rotates, CD, when it attaches to what, this end of the brush, what happens? This is positive terminal brush. This is negative terminal brush. So when CD segment is attaching to positive terminal of brush, the current direction changes, right? Current always goes from positive terminal to negative terminal. So current direction changes, that means previously here the current is going from A, B, C, D. Now when CD segment comes here and attached to the positive terminal of the brush, how the current direction goes? It goes from DCBA. When a DC segment comes here, it goes from DCBA, right? So when it changes the current, that means what? I'm changing the force experienced by the coil, right? When, for suppose, when CD comes here, this is CD, this is AB. One rotation over, this A segment AB went here, B, A. This is DC. After half a rotation, what happened? DC came here. When DC comes here, the polarity changes. Polarity changes means direction of current changes. Okay. So when the direction of current changes, what happens? The force experienced by the conductor also changes. Now here the CD direction is down. When it comes and attached to positive terminal, the current goes in this way. Previously the AB conductor is having the current inside the board. Now when it reaches this end, that means this coil is coming and attaching to this brush, to the negative terminal of the brush. What happens? The current reverses its direction because now it is starting from DCBA. Because this CD segment is going and attaching to the positive terminal of the brush. This is the positive terminal of the brush. Thus, it immediately changes the direction of what? Force. When it reaches this side, it acts as AB. CD segments acts as AB. That means it acts as, it is similar to the direction of the current inside the AB. When it started here, when the AB segment started here. When the AB segment goes there, how the CD segment behave in the beginning, it behaves in the same way. That means these brushes are stationary and this split rings helps in changing the direction of current because it is changing the polarity by transferring this segment and attaching to positive terminal half a cycle, and after half a cycle it is getting attached to negative terminal. So when this cycle is going on, the force is getting reversed every time because the current direction is changing. When the current direction is changing, the force is changing. Now, the same example, let us suppose this is AB, this is CD segment. This AB is experiencing force downwards, CD segment went up. At this point, what it does is, it changes the polarity. Now, this CD segment changes the current, this AB segment changes current. Thus, now it will experience a force downwards and AB will experience a force upwards. Previously, AB segment was experiencing a force downward, that's why it came down. Now it will experiencing a force upwards, it will go up. And thus it completes the full rotation. So this instrument, split ring, acts as a commutator. Commutator means it is a device which changes the flow of current, direction of flow of current. Right? It is changing the direction of flow of current. Previously it was going from ABCD. When it changes the coil, when it joins the CD coil here, AB coil here, it changes the direction of current inside the coil, right? Previously ABCD, the current direction. Now when the CD coil goes there and attached to positive terminal, what happens? It is coming from DCBA. Thus it changes the direction of current. So split ring acts as a commutator. Commutator means it is a device that changes the direction of current, and split ring here acts as a commutator because it is changing the direction of current. That's what we have written down. A device that changes the direction of current is called as commutator. Split ring here is acting as a commutator. See, this is a ingenious device, and this whole setup is very ingenious, right? Because I am passing electricity and it is rotating. So nobody is manually going there and rotating. So by passage of current, and we know because the current carrying conductor produces a magnetic field around it, and you have an external magnetic field, both together gives rise to force on this conductor which is trying to move it, and we constructed the instrument in such a way that one segment of this coil experiencing one direction of force, other segment of the coil is experiencing the force in other direction, which makes the coil rotate. The story does not end here. Now after half a rotation I have to complete the cycle, right? To complete the cycle, again I use this ingenious instrument device which is called commutator, which changes the direction of flow of current. That changing in direction of flow of current made this coil to rotate, to have a full rotation. Otherwise what? It will come and stop here. Because the force is acting on both sides, the force is constant. The force, to change the direction of force, we need to change the direction of current, which this device is making it happen. Right? Thus, we are successfully converting electrical energy into the mechanical energy. Mechanical energy means which is doing some mechanical work. Here it is rotating. Right? That energy is used to rotate this object. So this is how this electric motor works. To have a graphical view, let us go and see it. You can see here how it is at this peak point, the force direction is changing. You can see the split ring. Now the polarity will change. Now this part of ring is attached to the negative and the direction is changing. At the peak point you can see the split ring changes its polarity, the force's direction is changing. You can keep on watching how the flow of current is changing. Here at this point the direction of force is changing. At this point again the direction of force will change, so that it will go upwards. So it will facilitate to rotate the body. You understand? So from this is North Pole, this is South Pole. So in another configuration also you can watch here. See, here is the North Pole, here is the South Pole. The same segment is experiencing a force up here. Here it is experiencing a force down. So that's why it is having a full rotation. And why it can have a full rotation? Because of this instrument, what? Split ring, which we call as commutator. These are brushes. So the split ring keeps on changing the polarity of this coil. One time it is getting attached to the positive terminal of the brush. Second time it is attached to the negative terminal of the brush, which changes the direction of current. So how beautiful it is, right? You can see. Now, having discussed about this topic, we need to know about who invented this, right? William Sturgeon. After in 1800s, we saw the Volta invented the battery, okay? And then 1820, Oersted experiment. What he told, current carrying conductor is having a magnetic field around it. Now, after 5 years, in 1825, he invented first electromagnet, and also first working DC motor. They have previous versions of DC motor also. This is the first working DC motor which enabled to transfer 14 people from one end of the river to other end of the river using this motor. So how they look like? This is first electromagnet. This is the first DC motor. All right. So we have studied about DC motor in this. DC motor means direct current motor, which it is having what? The same direction. Now, what are the uses of this motor? You can see, if you want to print any material in a large quantity, you want to spread a newspaper, you want to give a newspaper, you want to run a printing press. What do you need? You need something that keeps on running, right? That keeps on rotating very fast and fast. So this motor helps us to run this printing press and motor vehicles and everything to run very fast, so that what happens, you can just think, if you want to give a newspaper, that means you are supplying a large quantity of information to large quantity of people. Right? Thus, that means the way of communication become very fast. Otherwise, what happens? If you Xerox something, you have to print something in large quantities. Somebody has to handwrite it. It takes more and more labor. It saves the labor now. Right? So it became a huge part of second industrial revolution, which took place between 1870 and 1914. Now also around us we use fans and tape recorders, motor vehicles, whatnot. This is all because of this phenomena, that force is experienced by a current carrying conductor when it's put under a magnetic field. How beautiful this phenomena is. Right? Now, one more question is, can the things work other way around? If a current carrying conductor is experiencing a force, if I'm passing the current, if it is producing a magnetic field around it, can changing in magnetic field produce a current? This is the question which they thought as dumb question was asked by Michael Faraday. A very famous scientist, Michael Faraday. We'll learn about him in the next session and discuss about this phenomena and how it works. If I vary the magnetic field in a coil, in a conductor, does it produce electric field? Think about it and come to the next session, and we'll discuss a beautiful phenomena in the next session and discuss about the famous scientist Michael Faraday, and let us get inspired by his story. Before going to end this session, let us answer these questions. I'll giving the questions. Please go after this session, sit down and close your eyes and think how the motor works, have a concept clear, and then write this on a piece of paper. And describe the working principle of an electric motor with a neat label diagram, right? Which we have discussed. You just revise it once more, go through your textbook, and then write neatly in your own words. What is the role of split ring in the electric motor? This is what we emphasize most of this session. So how this split ring helps electric motor in changing the direction of current. So many things it does. So one important thing, what it does in the motor, please emphasize on that. Write briefly, so that these two questions will summarize this session, and I hope you enjoyed this session. Thank you.